For as long as humans have looked at the stars, we've dreamed of reaching them. To cross all that darkness, reach one of those tiny lights scattered across the night sky, and someday stand on a world circling another sun. It might be the oldest dream we have, but there's a catch, and it's a big one. The rockets we've got right now are nowhere near fast enough. The same chemical engines that carried us to the moon and flung probes past Pluto are basically crawling the moment you measure them against the distance to even the closest star. And if we ever want to do more than just wave at our cosmic neighbors, reaching another sun won't take a bigger rocket. It'll take throwing out almost everything we think we know about travel. So right now, engineers are chasing ideas that sound flat out insane. Sails pushed by enormous lasers, engines that ride nuclear blasts, drives that bend space itself. So the real question isn't whether humanity goes farther, it's what kind of machine could actually take us there.
Let's start with a number that should genuinely mess with your head. The nearest star to our sun is called Proxima Centauri, a small red dwarf sitting about 4.25 light years away. That sounds almost reasonable until you actually do the conversion. 4.25 light years is roughly 40 trillion kilometers, around 25 trillion miles. Go ahead and try to picture that distance. You can't. I can't. Nobody can, because the human brain simply did not evolve to handle numbers like that. So let's shrink it down. Imagine the entire distance from the Earth to the Sun, about 150 million kilometers, squeezed down to a single inch. On that scale, Proxima Centauri would still sit more than 4 miles away. 1 inch to the Sun, 4 miles to the next star. That gap right there is the whole problem, and it's exactly why getting to Mars and getting to another star are not the same kind of challenge at all. Now you might be thinking, sure, but we build fast machines. We've got rockets and probes screaming through space. And we do. The trouble is that fast for us is painfully slow out there. Take Voyager 1, the little probe NASA launched back in 1977. It is now the most distant human-made object in existence, billions of kilometers from home, still quietly beaming back data from interstellar space. It's moving at about 17 kilometers every single second. That's roughly 38,000 miles per hour, absolutely blistering by any human standard. But if you pointed Voyager straight at Proxima Centauri and told it to go, the trip would take more than 70,000 years. Pack a big lunch. And Voyager isn't even our speed champion anymore. In December of 2024, NASA's Parker Solar Probe whipped around the Sun and hit about 192 kilometers per second, making it the fastest object humans have ever built. We're talking 430,000 miles per hour. And yet even that ludicrous speed is only about 0.06% of the speed of light. At that rate, the nearest star is still thousands of years away. Our absolute best is still a crawl.
So why can't we just bolt on more fuel and go faster?
This is where we slam into a wall built out of pure math, and it has a name. The Tsiolkovsky rocket equation, worked out by a Russian schoolteacher named Konstantin Tsiolkovsky all the way back in 1897. The idea behind it is simple and absolutely savage. To go faster, a rocket has to carry more fuel. But that extra fuel adds weight, and that extra weight means you need even more fuel just to push the fuel you already added. The whole thing snowballs out of control. Engineers literally call it the tyranny of the rocket equation, and tyranny is the right word. Look at the Saturn V, the giant that launched the Apollo astronauts toward the moon. Almost the entire rocket was fuel. Out of nearly 3,000 tons sitting on the launch pad, only about 45 tons actually made the journey. The rest got burned just clawing off the ground. And here's the part that really stings. Even our very best chemical rockets top out at around 0.004% of the speed of light. At that speed, reaching Proxima Centauri would take something like 98,000 years. So this is the moment everything changes. To reach another star, we cannot just build a bigger version of what we already have. We need a completely different way to move. And this is where things get wild. The first big idea flips the entire problem upside down.
Instead of dragging your fuel along with you, what if you left it at home? That's the thinking behind the light sail. Picture an incredibly thin, mirror-like sail, and instead of wind, you push it with light. Specifically, a giant array of lasers back on Earth, firing a focused beam at the sail and shoving it forward through space. Because the power stays on the ground, the spacecraft itself can be feather light and skip the fuel trap entirely. In 2016, this leapt straight out of science fiction and into a real funded project. A group of billionaires and scientists, including investor Yuri Milner, Mark Zuckerberg, and the late Stephen Hawking, announced Breakthrough Starshot, with $100 million behind it. The plan was gloriously bold. Launch 1,000 tiny chip-sized probes, each one attached to a sail just a few meters wide. Then blast them with a laser array pumping out around 100 gigawatts of power, enough to fling each probe to 20% of the speed of light. At that speed, a probe could reach Proxima Centauri in about 20 years, with another 4 years for its photos to crawl all the way back across space to us. A real mission to another star, inside a single human lifetime. It's a stunning idea. So where does it actually stand? This is the honest part. As of late 2025, Breakthrough Starshot has quietly stalled. Reporting from Scientific American described the project as on indefinite hold, possibly over, with only a few $million of that $100 million pledge ever actually spent. The physics was sound, the engineering and the funding crashed into reality. But the dream is not dead. In early 2025, a team at Caltech ran a beautiful little experiment, using a laser to physically push a sail membrane just 50 nanometers thick. That's a film so impossibly thin, it's measured in billionths of a meter, and they actually detected it moving on a scale of trillionths of a meter. So the core principle genuinely works in a lab, but there's still one enormous catch that nobody has solved. A light sail screaming along at 20% of light speed has no brakes. It would blast past Proxima Centauri and its Earth-sized planet in a matter of hours, snap a few frantic photos, and keep right on going into the void forever. Getting there is hard, stopping is a completely different nightmare. If pushing with lasers feels a little too delicate, the next idea charges in the opposite direction. Go nuclear. A nuclear thermal rocket uses a reactor to superheat hydrogen and blast it out the back at tremendous speed. It's roughly twice as efficient as the best chemical engine, and it's not just a sketch on a napkin. Back in the 1960s, NASA actually built and test-fired engines exactly like this under a program called NERVA. They worked. More recently, NASA and the military teamed up on a project called Draco to fly a nuclear thermal engine in space, with Lockheed Martin building the vehicle and a launch planned for 2027. It really looked like nuclear rockets were finally having their moment. But in 2025, that moment fizzled. Draco got canceled, zeroed straight out of the budget. A DARPA director explained that part of the reason was the price of ordinary rockets dropping so fast thanks to companies like SpaceX that the math behind the whole program no longer added up. The focus is now shifting toward nuclear electric propulsion instead, which uses a reactor to power ion thrusters. And those thrusters are wonderfully weird. A single one produces about as much push as the weight of a sheet of paper resting on your hand, but it can run for years, sipping fuel, patiently building up to incredible speeds. Basically, patience as a propulsion system. Now, if a reactor gently heating hydrogen sounds a bit tame, let me introduce you to the most insane propulsion idea ever taken seriously by actual scientists: Project Orion. The plan, dreamed up in the late 1950s, was to push a spacecraft by detonating nuclear bombs behind it. Real ones. You drop an atomic bomb out the back, let it explode against a massive shock-absorbing plate, and ride the blast. Then do it again, and again. It would have produced staggering thrust. It also would have showered the sky with radiation, so for fairly obvious reasons, it never flew. But the dream of riding nuclear power to the stars didn't die there. In the 1970s, the British Interplanetary Society designed Project Daedalus, a genuine interstellar spacecraft on paper. This thing was a monster, weighing around 54,000 tons, most of that fusion fuel, including helium-3 that would have to be mined from the atmosphere of Jupiter. Daedalus was designed to hit 12% of the speed of light and fly past a nearby star in about 50 years. It was never built, but it proved something important. Reaching the stars within a single lifetime isn't physically impossible. It just demands energy on a scale we can barely wrap our heads around. That fusion dream is still very much alive today, and it's often called the holy grail of space travel. Fusion is the same process that powers the sun, crushing atoms together and releasing staggering amounts of energy. Pull it off inside an engine, and you'd have something far beyond anything we currently fly. A British company called Pulsar Fusion is openly working on a fusion drive they call Sunbird, and in early 2026, they announced that their test rig had produced its first plasma. Now, full honesty here, because this part really matters. That was ordinary plasma, not an actual fusion reaction. And a Princeton lab chasing the very same goal has only managed to hold its plasma together for fractions of a second. The truth is, no fusion engine anywhere on Earth has ever produced more energy than it consumed, and not one has come close to flying. It's hugely promising. It's also still firmly stuck on the drawing board.
And if fusion still isn't extreme enough for you, there's antimatter. When matter meets antimatter, both are instantly annihilated, converting almost all of their mass directly into pure energy. Drop for drop, it's the most concentrated fuel in the entire universe, around 100 times more potent than fusion. In theory, an antimatter rocket could reach an astonishing 40% of the speed of light. So why aren't we already building one? Because antimatter is the single most expensive substance on Earth. Estimates for producing just 1 gram of it run from tens of billions of dollars up to numbers so enormous they basically stop meaning anything. And right now, all of humanity combined produces only a few billionths of a gram per year. At that pace, fueling a single starship would take longer than the universe has even existed. So antimatter is real, it absolutely works, and it's almost comically out of reach. There's one more clever idea worth knowing about, because it tries to fix the light sail's biggest weakness. It's called sunbeam, and instead of pushing a sail with light, it fires a beam of electrons traveling at nearly the speed of light. Electrons are easy to whip up to incredible speeds, and the platforms doing the firing would sit close to the sun, soaking up its raw power. On paper, a beam like this could shove a probe to 10% of light speed and send it toward the Alpha Centauri system in just over 40 years. The hard part that nobody has cracked yet is how the spacecraft turns that incoming beam back into forward motion. But it shows just how creative this whole field has become, hunting for any possible way across the gap. Okay, we've done lasers, nuclear blasts, fusion, and antimatter. But I know exactly what a lot of you have been waiting for this entire time. What about warp drive? Going faster than light itself. This is the wild part. It's not completely impossible on paper. In 1994, a physicist named Miguel Alcubierre found an actual solution buried inside Einstein's equations. The idea is genuinely mind-bending. Instead of moving the ship through space, you move space itself. You sit inside a calm bubble while space contracts in front of you and expands behind you, carrying you along faster than light, without ever locally breaking the cosmic speed limit. It's beautiful. It also comes with a catch the size of a galaxy. To bend space like that, the original math demanded a bizarre kind of negative energy, exotic matter that we have never found and may not even exist. And the amount needed was, at first, comparable to the entire mass energy of the observable universe. Slightly inconvenient. Over the years, theorists chipped that number down, and in 2024, a research team published something genuinely interesting. A warp design that, for the very first time, works using only normal, ordinary matter. The honest catch, and it's a huge one, is that their version travels slower than light, and it still requires a mass equal to several Jupiters.
So warp drive remains real mathematics and pure fantasy engineering. Don't go booking the trip just yet. So if we can't bend space and we can't go nearly fast enough to make the trip short, there's one last option that's almost romantic in how stubborn it is. If you can't shorten the journey, just bring everything you need to survive it. This is the idea of a generation ship, a vessel so enormous that it becomes a tiny moving world where people are born, live their entire lives, and die in deep space, so that their distant descendants are the ones who finally arrive at another star. In 2025, a design competition produced a detailed concept for exactly this, a spinning cylindrical world ship nearly 58 kilometers long, built to carry a few thousand people across the dark over many centuries. Researchers even argue about how many passengers you'd need to keep a healthy population alive for that long, with serious estimates ranging from as few as 100 carefully chosen people all the way up to tens of thousands. At that point, it's not really a spaceship anymore. It's a civilization with engines. So, after all of that, where does this actually leave us? Let's be real and honest about it. A small robotic probe reaching another star is genuinely plausible this century, if the money and the engineering finally line up. Sending actual living humans is almost certainly centuries away, and warp drive, despite all the breathless headlines, is simply not on the horizon at all. But this is the part that makes the whole story matter. Crossing to the stars was never going to come down to one lone genius and one magic invention. It's a relay race run across generations, where each team shoves the baton a little farther than the last. That's literally the motto of one real interstellar research group, to the stars in ever-expanding steps. And it's worth remembering this. The Voyager probes are each carrying a golden record, a message from all of humanity, and those records will keep drifting through the galaxy for over 1 billion years, long after every monument and city on Earth has crumbled into dust. We've already flung a piece of ourselves toward the stars. Now we just have to figure out how to follow it. And honestly, maybe that's the most exciting part of all of this. We are genuinely living in the era where humanity stopped just dreaming about reaching other stars and actually started running the experiments, doing the math, and building the very first pieces. The nearest sun is still impossibly far away. The machine that finally takes us there might not even be invented yet, but somebody watching a video exactly like this one could turn out to be the person who cracks it. So here's my real question for you. Out of everything we covered today, the laser sails, the nuclear rockets, the fusion drives, the warp bubbles, which one do you actually think gets us to another star first? Drop your pick down in the comments because I genuinely want to see what you all believe. And if staring into deep space and asking gloriously impossible questions is your kind of thing, hit that subscribe button and stick around, because we are honestly just getting started. Thanks so much for watching, and I'll catch you in the next one.